About 3 things to discuss with capacitance, and we're going to go right into electric circuits.
I'm weighing at resistance right now.
It's always quiet in here after the kernel.
It's right out there.
Over that. I feel like he should have a nest, and he should just be able to sit in class and take notes.
You put them up on the roof.
Put them right up there.
Better if you could pop out some eggs out of them, fry some eggs.
Okay, so let's see. What is it we can say about capacitors that are important?
Oh, look, a squirrel. No, just kidding. Okay, so to begin with, calculation of capacitors. We've talked a lot about capacitors, so we'll start with functionally. Calculation. I'm so used to spell just filling that in, right? Now, by the way, with the thing about it is capacitors are essentially a physical scenario. They're a defined system. There is no necessity, of having an electric charge or electric potential. The capacitance just defines the interaction between two interacting but non-contacting conductors. Okay, so when you calculate a capacitance, one thing to kind of keep in mind is you're never going to have an explicit reference to electric charge or voltage or otherwise. However, we do note that functionally, to calculate capacitance, it is in fact described as Q. I'm going to put delta V because it's, oh, you know what? Let's just call it V because it makes the calculus a little bit easier. So I so prefer using delta V, but in electric circuits use V anyway. But it's never potential, it's always relative potential. Okay, so functionally this is what it always is. The question is how do you use it? And therein is the trick to most of these problems. Secondly, we need to associate the work to charge a capacitor, and ultimately the associated stored potential energy. That's the second fundamental line item, if you will, as far as skill sets to deal with in this particular topic. And then the third is combinations. When you have combinations of capacitors, you can establish a net or effective capacitance. Equivalent capacitance is probably what the word I would use. So these are really sort of the keys. And of course, certain applications along the way. So let's start with how you calculate capacitance. In a perfect world, you just measure voltage and charge, right? And that's sort of the easiest way to do it. You just have a way of making those direct measurements. But analytically, we have a way of calculating it from fundamental principles. And the idea is functionally this approach. So typically we use, why don't we say it this way? we establish an equation for an electric field between the conductors. Now we'll use as an example parallel plate capacitor. Now, to this end, if you're not memorizing, really it comes down to usually an application of Gauss's law, or at least a direct Coulomb law calculation to get the electric field relationship. So I'm just going to draw the capacitor this way, and we'll establish that this capacitor has a certain width. I'm going to call it X. And there's phase 1, phase 2. And if we have a positive charge, Q plus, a negative charge, Q minus on the opposite side, and this thing has a certain surface area, so we've got something to work from. It's supposed to be just put it here. Okay, so it's a parallel plate capacitor. We've seen this a number of times already. The first thing you do is you establish an electric field between them. Then you calculate the potential difference in terms of its relationship to electric field. Where V, if you will, go from one side to the other, is related to evaluating E, if you will, dr. And all I care about is the absolute value. In fact, I'm not going to write that one. I'm just going to write it this way. So even though there's a minus out there, I don't care about the minus sign. I want the absolute value of the number. Because it's about capacitance, right? The charge and the V would vary depending on which side you look anyway. So you end up having to evaluate this based on this equation, and that's a key. Once you have that, then the third part is to then solve the relationship C is equal to Q over V, where this is your equation for V, and Q is its relationship to any particular voltage between the plates, or between the conductors, I should say. And I'm going to make one little trick, and this is usually the trick to doing these problems, is that you note, because V will typically be expressed in terms of the charge, the Q's will cancel out. And you want to make sure that they cancel out between the numerator and the denominator. So it's a pretty straightforward approach. It's just relatively long because you have to start by getting an electric field. We spent a lot of time, 2 full chapters on, in a way, 3 chapters almost on electric fields. And then we use that to evaluate the integral, and then we move on. So in the case of a charged capacitor of this particular type, we'll just use this as an example. And let's, 1, 2, 3. So it always goes basically the same way. So we'll assume that there is a particular voltage, V, between the plates of these capacitors, or these conductors. So we know what the electric field is. I'm not going to go through Gauss's law, but we could always do Gauss's law and use that as sort of the easy answer to get there. But I know that between the capacitor plates, the magnitude of the electric field is a constant quantity. And it's related to the surface charge density and the effective dielectric constant. Notice I'm using the effective dielectric constant. And we have the charge density. So it's Q total, if you will, divided by the area A. And epsilon is the effective permittivity constant, which would be related to the dielectric constant times epsilon naught. And if it's just air between the capacitors, or between the plates, it's just 1. Cap is 1. So I'm just going to keep it generic because so I don't have to introduce this dielectric constant later. So we have this electric field, and it's going to run positive to negative, except on the edges. And as long as the surface area is relatively large, separation distance is small, that outer fringing is negligible. Not that it doesn't exist, it's just negligible compared to the bulk of the electric field inside. So, according to step 1, applying this approach, well, that is 1, I should say. We need to calculate V from this. And the way we would do that is we would say that potential difference between one side and the other should be related to integrating E, in this case, dx, as we go from one side to the other. And I guess we can just call it from 0 to x. I'm always bad about using dummy variables for the x. I just integrate dx and use x simultaneously instead of a prime. And there's a minus sign here, but all I care about is the magnitude, because I'm going to express the potential as a number if I were to measure it. But aside from that, I just want to know how it directly relates to the electric field and space. So in this particular case, E is a constant, so E comes out anyway. And so we're basically left with the potential difference from one side to the other corresponds to the electric field times x. In other words, it's a linear relationship. Or sigma over epsilon times x, where you have your separation distance x. That'd be step 2. That's it. It's more complicated and you've got to deal with it, but ultimately this is what we're concerned with. Now, step 3 is we solve for C, which is equal to Q over V. And for this particular set of geometries, if you will, the capacitance would be equal to Q divided by sigma over epsilon times x. Nope, that's upside down. Yeah, no, that's right. That's right. Which we could just as easily write as Q over Q epsilon A. Another way of writing the charge density times x. There's where the Q's cancel out. That's the trick, is get rid of the damn Q's. Basically, it's chapter 24, solve for potential, and then put it in the inverse and divide out the Q's. Everything else is your capacity. And so what we're left with is something familiar, hopefully, which is how we previously rationalized the parallel plate capacitor relationship to surface area and separation distance. It's pretty straightforward. The key is just basically heavy reliance on chapter 24 and calculation of electric potential, which is why we spent a decent amount of time on that and talking around capacity. So the question is, that's the trivial case, right? What do you do when the problems are not quite such simple geometries? Same approach always works, but how do we apply it? So this is what I'd like you guys to do. This, that, here's what I want you to think about. We're going to look at concentric cylindrical conductors. Doesn't have to necessarily be hollow. And so we'll have one on the inside, actually is larger, that has a radius R1. Surrounded by a second conductor that has a radius of R2. And then this thing is a certain length, L. Okay, this is an example of essentially a coaxial cable, if you will, like we used to use for television signals, and I don't know if we still do, we use them for other things as well. So this is our example. So ultimately, what I'd like you to do is maybe use Gauss's law or otherwise, and to make life easy, let's assume that the inside is ground. We got minus there, and the outside has a positive charge, so it's a positive cylinder. It's on the outer edges, assuming it were charged in some way. And there's a certain potential difference between the ends when it's charged. So, solve for E, first of all. Gauss's law is probably the easiest approach. To make life easier, if you want to make it the simplest Gauss's law problem as possible, let's just make an assumption that L is much, much larger. So it's a very long relative to R1 and R2. That'll make life a little bit easier. So I'm going to go grab a cup of coffee, maybe clip my toenails. Feel free to go to work. Run up to the store, pick up a bag of chips or something. And I come back and you're all done. So, think about it, brainstorm it, lay it out. Epsilon R. I think that's it. So it's inversely related to R. Now before we had a lambda, because we just assumed that it was a point of charge. Now we don't have a lambda, but rather we have a sigma, so we have a charge density. But this then we could rewrite as Q total R1 over the area, which would be, what would we have here? The area of that charge would be 2 pi R1 times L and an R. And the, oh, and I'm leaving out an epsilon. So I'll put that epsilon in there. So the R1s cancel. And if we look very closely at this thing, Q over L is lambda. So there really is a linear charge density built into this calculation, believe it or not. But it would be Q over 2 pi L epsilon R, as long as you're between R2 greater than R, which is greater than R1. So as long as you stay there, that would be the expression for the electric field. Radial symmetry away from the center, cylindrical radial symmetry. And by the way, in this case, it wouldn't be dx, it would in fact be dr. Previous example, we could get away with simple geometry. Did you guys get to that far? You shaking, Steve? You like?
I made a mistake.
But does this seem at least clear as dirt?
Yeah.
Okay, just making sure. So, plug this into here. And we have integral of Q 2 pi L epsilon. All of those are constants. And then we have R in the numerator, in the denominator, dr, as we go from R1 to R2. And we just make this an absolute value. I just don't want that minus sign to have to deal with that. There's no point to it. We take all the constants out. And we're left with the integral of dr over r. So we're going to have a natural log, r2 over r1. That would be our potential difference, our voltage expression. We solve for C. Again, I wanted that Q explicit because I know it's going to come out of there eventually. So we're left with Q over 2 pi L epsilon. And we have the natural log of R2 over R1. Again, we can divide out the Q's. This Q will always depend on V. So if you don't have an explicit description of V as a number or a value, then you shouldn't have a description of Q necessarily. So we're left with something that looks like 2 pi L epsilon over the natural actual rod of R2 over R1. And it might not be a bad idea to do a spot check and make sure that the units of that are consistent with, if nothing else, a parallel plate capacitor, just in principle. So we know that our units ought to be something that looks like a Coulomb per volt, or Coulomb squared per joule, or a Coulomb squared per joule.
Yeah, just epsilon naught. Okay.
Kinds of fun variations.
The effective.
Mind reiterating step one and
Yeah.
how you ended up where you did?
Yes. Or let me, no, I don't mind.
Okay.
Okay. So, first of all, because we have a conductor inside another conductor, as long as I'm looking in between them, I don't have to consider the outer conductor at all. So what I'm left with is, I've got some conductor of some length and some radius, and I want to know at some point out here what the electric field is, a distance away, I'm going to say R, where R is larger, it's that distance actually, it's always from the center. So I would make a Gaussian hypothetical cylinder of some smaller L. And calculate the electric flux over this. So Gauss's law then would argue that the electric flux should be equal to, now we've got technically three surfaces. We've got the flat face surface on either side, and then we've got the shaft surface. So really we have, if this is surface 1, and then the inside is surface 2, and then we have surface 3 here, like that. So the total flux would be a combination of the flux through surface 1 plus the flux through surface 2 plus the flux through surface 3. And as long as we stay somewhere in the center, and this thing is long enough, then we can ignore the little craziness that happens near the edges, because it'll be tiny compared to the electric field that's contained inside. Yes?
Where was it where if it went through the top and the back, it was 0 RDO?
There's no top and back, but there's the two sides.
The two sides, the
Yeah.
front and back.
So if you're, I'm sorry, front and back, yeah. So if this is your surface, your normal for this surface, that's the A vector, if you will, is pointing this way. But the electric field is pointing,
Always normal to it.
normal to it at all points.
So the dot product's 0.
And the reason why we can justify that is that we can say, if this were in fact a positive charge and you have negative charges here, the charges will always run positive and negative. Or, I've got the e's backwards to make that plus this minus 3. So it would run positive and negative for all of those charges. Now these charges would be spread out more than they are inside, but they'll always go positive and negative if you've got equal and opposite charges. So that's my justification for getting rid of these two, and that would be the same on either surface.
Right. I wasn't sure if you were going to do that or not.
Yes, we would need to. And that was why I was explicit to say L is much larger than R1 and R2. So we can ignore that. And if it weren't, then it still probably wouldn't matter unless you were looking at a tiny little peanut-sized shape. So this is what we're left with. And then we can say, well, however we want to calculate this along this face,